Ooh, that's loud. Okay, so to start with, this is a review. Like, this is just practice. There's nothing new on that top half of that page. So just work those as kind of a warm-up to get your brain back into visual, graphical limits. And then we'll pull popsicle sticks for those in a minute. I fix, this should probably just be x approaches -2, not with the plus sign. That way it's an overall limit and it fits the pattern of the first one. Limit from the left, limit from the right, overall limit, and then function value. It should be review. It looked like everyone got them all right. At least everyone I called on got them right. So pretty simple. I think you got the idea of limits graphically. Now we're going to go back to algebraically, but one-sided limits algebraically. So yesterday was algebraically, but not one-sided. Today, algebraically and one-sided. One-sided limits are more obvious when a graph is provided. Yeah, definitely, because then you're just looking at the picture. You got to the point now where a limit, while given a graph, should be pretty easy. You just understand what you're looking for. Simple. But when you want to find a one-sided limit of a function given an equation, it can be a little trickier. Now, we've done substitution before, and so that continues. What's a little bit different now is the plus or the minus, because now we've got one-sided limits. The good news is, when you do the substitution, you ignore the plus or minus thing, the little exponent-y. It's not an exponent, it kind of looks like an exponent. You just plug in the number and don't worry about the plus or minus thing. And if you don't get a 0 in the denominator, like as long as you get a reasonable answer, then you've got it. The plus minus thing didn't matter. So kind of like yesterday or Tuesday, first go is substitution, and first go is substitution ignoring the plus or minus, and just see if it works. So if I plug in 2, again, I'm not worried about the plus or minus yet. Let's just plug in 2. So that'd be 0 over 8. That's equal to 0. That's nothing wrong with that answer, so we're good. As you might guess, that doesn't happen often because we want to force you into the tricky cases to test your algebra. All right, as x approaches 3 from the left. Again, first step is just to kind of ignore the minus sign and just plug in 3 and see what happens. So 4 minus 3 is 1. 3 times 9 is 27. Nothing wrong about that answer, so we're good. One more that I think is going to work. This is just to review our trig skills here. Again, first go, ignore the plus minus, just plug it in, and we'll review our trig skills here. When I ask Brooke for the sine of pi over 3, I even draw the picture for you. That helps. That's what helps me. You're saying the right numbers, but not.
Oh my gosh, I'm so tired. I'm so sorry. Square root of 3 over 2.
There you go. Root 3 over 2. And then Jace, how about the cosine of pi over 3? 1. Good, 1/2. And that's a safe stop. So why risk messing up fractions and square roots and fractions? Just leave it alone. Okay, those are the easy cases. So most of the time, it's not going to work that way. If we're going to make them tricky. Most of the time, you're going to get a 0 in the denominator or an indeterminate form. And so you're going to have to do some more thinking. So if I plug in 3 to this one, 3 minus 5, that's fine. -2. 3 minus 3, that's 0. Can't divide by 0. So something strange is going on this one. Let's see if we can figure this out. And this page is where things get a little bit weird. Don't know how else to say it. Plug in a slightly larger or smaller number. Another way to say that is, now we have to consider the plus or the minus. So first pass is just plug in the number and see if it works. If it doesn't work, then you got to consider that little plus or minus on there, because now it matters. If you get a non-zero number in the numerator and a 0 in the denominator, you have a vertical asymptote. That's what happened on that the last page before we turn the page there. Right? This thing has a vertical asymptote at x equals 3. Thinking back to our pre-cal days. But a vertical asymptote, right, could be going up, could be going down. So that's what we've got to figure out. We'll need to determine if our answer is going up to positive infinity or going down to negative infinity. To do this is where things get a little bit strange. Plug in a slightly larger number if it's coming from the right? Because the plus sign would mean make the number a little bigger. Or a slightly smaller number if your limit is coming from the left, right? The minus sign means a little bit less than the number, left of the number, something a little bit smaller. And you want a number that is really, really close to the given number. Okay, so if I plug in 3 from the right, the first go would be 3 minus 5 over 3 minus 3, negative 2 over 0. Okay, so that doesn't work. Now I need to plug in something closer. Do I want to plug in something a little bit more than 3 or a little bit less than 3? More. Why more? Because the plus. So I need to plug in something a little bit more than 3. So let's plug in. And the good news is you only have to worry about the 0 stuff. So the top you can just leave as 3 minus 5. We're not really worried about that one. The problem is the 0. So a little bit more than 3. So somebody give me a number that's a little bit more than 3. 4 is too close to 3. I want smaller than that.
3.001.
There we go. I like that. 3.001. Now you could get closer to 3, right? You could do 3.0001 or 0.0001. You get the idea. Let's see what happens. So 3.001 minus 3 would be 0.001. And I don't need a calculator because this isn't the exact answer. But what am I headed toward if I do negative 2 divided by a really small negative number, a really small positive number? Negative infinity. Negative 2 divided by a really small number, I'm headed toward negative infinity. And we're not going to show all these steps every time, but if I had plugged in 3.0001, then I'd be dividing by 0.001, and I'd be even further along my way toward negative infinity. Let's try the next one. 4 from the left. Well, first go is, don't care about the left, let's just plug in 4. 4 minus 5, 4 plus 2, 4 minus 4. Already we see there's a problem because you got 0 at the bottom. And the top I've got negative 1 times 6 over 0. That's not going to work. So I need a number slightly less than 4. Yeah, how many 9s do you want to put on there? That's up to you. And again, the only thing that is a problem is the 0 stuff. So I'm just going to leave the top as 4 minus 5 and 4 plus 2. I already know that that's negative 6. Bottom, less than 4, 3 points. And we'll do 4 of them. Or 3 9s. It doesn't matter. You can do 2 9s, you can do 1 9, you can do 8 9s. the idea is when you do 3.999 minus 4, what am I getting? Something small. Negative, though, is the big deal to be careful of. It's definitely going to be negative, and it's going to be negative really, really small. 0, 0, 0, 1. Carry that right. It doesn't really matter if I carried it right because I just know it's going to be small. So what's negative 6 divided by a negative super small number? Positive infinity. So the idea of plugging in something a little bigger or a little smaller helps you figure out, is it positive infinity or is it negative infinity? Now, you start to get the hang of this, and rather than plugging in 2 first and like writing it in, you just kind of visually look and see, is 2 going to mess this thing up? Is 2 going to mess this guy up? Yes. So that means I need to plug in something a little more than 2. At least right there. Everything else I can just use a 2. 4 minus 2, 7 plus 2, 1 plus 2. And then now I've got to be real careful in this last one. If you're careful, I hesitate to show this. If you want to write in 2.0001, that's fine. What some people will do, and this messes with some people's head to write this, you can just write in, you're like, well, I'm going to substitute in a little more than 2. That's what 2 plus means, right, is a little more than 2. Let's see if we can handle that in a minute. 4 minus 2 is 2, 7 plus 2 is 9, 1 plus 2 is 3. What's 2 minus a little more than 2? Yeah, negative 0.000 something. And that's kind of all you need to know. The something doesn't really matter because it's so small that we're headed toward infinity. Are we headed toward positive or negative infinity on this one? Negative, because I got positive, 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 negative, so negative infinity. So do show your work on these, but how you show the work, you can actually plug in a number that's bigger or smaller, or you can, literally substitute the thing that's in the bottom. And then again, that kind of messes with some people. They're like, 2 minus 2 plus, what are we doing? But you understand that 2 plus means a little more than 2. So 2 minus a little more than 2 is negative. And that's the big thing on these is, you're getting 0 in the bottom, but is it a little more than 0 or is it a little less than 0? Because the thing we're concerned about is the sign. Is it positive or negative? Sometimes, if you know the graph, you can turn it into a picture problem rather than an algebra problem. Although this one's not that bad. If you plug in something a little less than 0, you're headed toward negative infinity. But if you remember what this graph looks like, this is what we're doing in Algebra 2 right now. Do you remember what the reciprocal function looks like, or the rational payment function? Remember what that shape looks like? It's hard to follow your hand gestures.
I'm more doing it in front of myself.
Something like that. So if we're approaching x from the left, we're over here, and we're headed toward negative infinity. But even that one is probably easier to just say, why don't I just plug in something a little smaller than 0, and I get negative infinity. So if you can translate the function to a graph, maybe that makes it easy, but it's not often you can translate one of these to a graph, right? Especially those 3 examples we did. Like, no one knows. I mean, you could figure out what those graphs look like, but that would take way more work than we did. All right. Even after you do the 0 plus 0 minus stuff, you still might get an indeterminate form. So even after you do the trick of 2.99999 or 4.00001, you still might get 0 over 0, infinity over infinity, negative infinity over infinity. And then you use normal in quotes, like what's normal in calculus. You use those three methods that you used that we learned on Tuesday. Factor and reduce, simplify a complex fraction, multiply by a conjugate. And we're not even going to do examples here because it's the same thing you just did. Seth.
And then once you do one of those steps, then you just plug in the number. No, ignore the plus or minus.
Correct. Then you sort of repeat the process. You remember every time you do this, something will reduce and simplify. And then you're right, you'll try to substitute again. Hopefully without the plus or minus. And then if that doesn't work, you'll have to substitute with the plus or minus. That's a little misleading the way I drew that, right? Because if it works without the plus or minus, then you got your answer. If it doesn't work, well, then you got to consider the plus or minus stuff again. All right, this last step is something we've done before. Let me tie it to what we did before. Maybe that'll make the connection here. For limits when x is going to infinity. Well, in pre-cal, when x was going to infinity, we didn't use that verbiage. But if we're headed toward infinity, we might be looking for a horizontal asymptote. Only need to consider the highest degree term in the numerator and the highest degree term in the denominator, and then reduce. Right? Because if x is getting really big, let's look at our first one here. As x gets really big, one of these terms in the top matters a whole lot more than the other terms. Which one matters the most of the top terms? Yeah, the cubed. And how about of the bottom terms? Again, the cubed. So those other terms won't matter when we get out to 1,000 or 1,000,000 or a gazillion. Or x cubed over 5x cubed. Well, that's convenient. The x cubes cancel, and I'm left with 4/5. Number 9s. Click on some people here. Oh. Evan left us for BC. Lexi's not here today. Justin's not here today. Jimmy's back there. Okay, Ava. I think a simple question. Which term matters the most in the top if we're going to infinity? Although, be careful. Read all the terms carefully before you answer that question. Which term matters the most in the top? We want to get the highest degree term. That's the one that's going to matter the most if we plug in 1,000 or 1,000,000. So which term is the highest degree term in the top, Ava? The x to the 5th. Okay. And the only reason that one looks confusing maybe is they wrote it out of order. So be careful. If it's written the right way, like in descending order, then it's the first term. But if we intentionally try to mess with you, make sure you're reading all the terms. Jimmy, how about the bottom? Which term is the biggest, or the one that we're most concerned with? The cube. Okay, so those won't cancel, but they will reduce. So negative 2x squared over 7. So if I plug in infinity, negative 2 times infinity squared divided by 7, I'm headed toward negative infinity. Right, and the last one, again, just to call on some people. Ashlyn, what's the biggest term in the top? X to the 5th. Again, kind of buried back there. Christina, the biggest term in the bottom. 7x to the 6th. Again, intentionally out of order to force you to pay close attention. It won't cancel completely, but 5 of them will go away anyway. So 1 over 7x. And if I plug in infinity, 1 divided by 7 infinities is, if I have $1 and I divide it up by 7 times the population of the earth, yeah, everybody's getting $0. Now, that's pretty easy, but there's a saying that goes with it to make it even easier. Do you remember the saying, Ashlyn? Top no, bottom O, equal co. And the question that saying is answering is, where is the biggest degree? If it's in the top, then there's no limit, although we've got to be a little bit careful here. Officially it's D and E, but you'll have to consider, is it positive or negative infinity? And I don't mean it's both, I mean you've got to figure out which one it is. So the saying, I mean I guess it still works, but there's more work to be done. If it's top no, you've got to figure out positive or negative infinity. If the bottom is bigger, then you're headed to 0. If the exponents are equal, then you use the coefficients. That might not even be worth it because it's not really that hard even without the saying. Top no, bottom O equal co, but be careful with the top no. It is a no, but we want to be more specific about which no it is, which infinity it is. So I don't know if there's a way to make that rhyme better. Probably not. How to say all that in a rhyme. Top, positive or negative infinity, bottom O equal co. Doesn't have the same ring to it. Okay, easy day today. So let's look at worksheet 3. Easy notes day today, especially for a block day. And let's get started on worksheet 3. And I will be happy to help you.